Yesterday, I began to discuss a little bit. Also, I had made a choice of cosmological probes that we could use to test the nature of dark matter, and in particular to test the mechanisms that I have been discussing in the three first lectures. Among these probes, I had mentioned that we could use cosmic microwave background. Okay, cosmic microwave background, first of all, is probing very well the amount of matter we have at cosmic scales. We also, thanks to cosmic microwave background, among other things, we can actually probe energy injection of dark matter at that time, or even, before that time, that at the end of the day give rise to some change of ionized level. And this affects the cosmic microwave background and put constraints even on the standard weakly interacting massive particle. It's the vanilla WIMP that annihilates through S-wave annihilation cross-section. Okay. Interestingly, late-time probes like Lyman alpha forest, okay, which is there, which has the data, can put extra constraints on the energy injection in the form of heating of the intergalactic medium at late times. On the top of this, we have future probes, which hopefully will really probe cosmological sources of perturbation in the 21 centimeter signal, okay, that could help to improve actually significantly on dark matter energy injection at late times. This includes, for example, dark matter decays, okay, just simply through the redshift dependence that I have mentioned at the beginning of the lecture yesterday. You essentially could see that you expect dark matter decays to be more affecting your history at late times. Same thing happened for P wave annihilating dark matter, just because it's P wave suppressed, it's super velocity suppressed, but at late times you have a boost of structure formation, a boost of annihilation due to structure formation. And this is extremely relevant in the case of P wave annihilation because you have no constraint at early time. Actually, you don't have the constraint that comes from CMB, or they are very irrelevant, let's say. You have, but they are irrelevant. Now, if you want to look at the late time story for P-wave dark matter, which I didn't mention, the problem is really to treat correctly the astrophysics, okay, the boost from structure. And to my knowledge, up until now, this has not been studied in details, but I know that people are working on that. Okay, so that was for dark matter energy injection, and I think I mentioned, if not, this is the lecture today, I would like to discuss the non-cold nature of dark matter. So by non-cold, I mean essentially anything that is going to modify my linear matter power spectrum at small scales and give rise to a suppression that could, for example, be similar as the one that we have with thermal warm dark matter. So essentially, this is going to go back to some concept that I have mentioned also some lectures ago, where you had the thermal warm dark matter production, which implied some particular dependency of the relic abundance of the dark matter in the mass of the dark matter and the number of degrees of freedom at the time where dark matter decouples from the plasma. Okay. Thermal warm dark matter is going to suppress the amount of perturbation you have on small scales due to this free streaming, that it has non-negligible velocities at the time of structure formation, okay? And this gives rise to certain scales over which it can free stream. That depends on the property of the dark matter. We will go through that in a few minutes. And this gives rise to a suppression of the linear matter power spectrum. If you want to go to whatever observation at late times, you have to go to nonlinear evolution, okay? You use n-body simulation, hydrodynamical simulation, and so on, okay? Here, I will only give you information about the linear power spectrum and tell you essentially how we are going to be able to reinterpret, in certain cases, the results that have been derived for thermal warm dark matter into some other scenarios, okay? And tell you essentially when you cannot do that too, okay? Another kind of, I think I mentioned that in the previous lectures, another mechanism that can give rise to a separation of the power spectrum is that your dark matter essentially interact with light degrees of freedom, okay? It could be dark photon, it could be neutrinos, okay? Dark matter interacting with neutrinos is fully allowed, and this can give rise to essentially suppression of your power spectrum due to essentially dark matter, as baryons and photons that interact give rise to a source of pressure due to this interaction into the baryon plasma. You can have the same for dark matter due to its interaction with the light degrees of freedom, okay? Good, so let me begin with the, let's say, standard suspect for non-cold dark matter. So the standard suspect is the so-called thermal warm dark matter. Thermal warm dark matter for which you want to essentially evaluate what is the free streaming scale that you hear usually in the literature. And the point is that, I mean, you will take different textbooks or different papers and everybody has his own definition of the free streaming scale, okay? Here in particular, I will essentially, just for this part, follow what you can find in, for example, neutrino cosmology, which is a book on neutrinos only, essentially, not only on neutrinos, only on cosmology and neutrino physics. So, for this, I'm just going to go back to the growth equation of non-relativistic dark matter that I mentioned several times in the lectures, okay? So, you get this equation by combining perturbation density evolution with velocity density perturbation evolution. You combine them into one single equation that give you the double time derivative of density perturbation. It gets a friction term due to Hubble rate expansion. And here you have this contribution that essentially gives you the pressure force that enters into the game and the gravitational forces, because h squared is just proportional to the amount of matter you have in your universe. And I'm working here. I'm going to essentially look at what is happening at the time where structure forms. So we are no more in radiation-dominated era, more in matter-dominated era. Okay, so 3h over 2 delta k equals 0. So free streaming scale in this context is defined as essentially the scale where these two terms equals. This is one of the definition that you will find in the literature. So the free streaming scale, which is the inverse of the wave number that enters here, when you equate these two equations, is just 2 pi 2 over 3 square root velocity divided by the Hubble rate. Now, essentially, you can go back to this equation and think of what is exactly the velocity term that should enter here. But what you will find in the literature, let me just tell you what you have typically found, is, okay, this velocity is typically going to be the typical momentum, the average momentum over the distribution that you have. Thinking of thermal warm dark matter, the average momentum is very easy to compute, okay, with Fermi-Dirac distribution. And you will get that this is 3.15, the temperature of your dark matter divided by the mass of the dark matter, okay? You plug this into your equation, and you recall that for a particle that has decoupled in the early universe, and that while it's still relativistic, its temperature is going to scale as 1 over a for some time, okay? So what we are going to use is that take I from the moment it decoupled, and essentially, okay, up until the moment it became non-relativistic, but which can be, as a first approximation, considered as, let's say, up until today, is the decoupling time divided by the scale factor. As a consequence, you have a free screaming scale as a function of the redshift. You take this scale factor into account, that scale factor into account, and you end up with 0.076, 1 plus z to the minus 2, h of z divided by h naught. It goes as 1 over the decoupling time temperature, okay? To get this number, I have inputted the decoupling temperature of the neutrino, which is MeV scale, times the mass of the dark matter expressed in kilo electron volt, okay? And this is in megaparsec minus 1. Okay. So this is essentially illustrating the usual statement that you might hear that KeV dark matter is a dangerous quantity, it's a dangerous beast, it's a dangerous non-cold dark matter, because it's typically going to give rise to free screaming scale of the order of megaparsec, okay, today. And we have structure at this level, okay, we have to go through nonlinear perturbation evolution, but yet this is not acceptable. Problem is that this information is usually just simply kept in mind as KeV dark matter is excluded, okay? KeV dark matter is too warm. But this is only strictly valid in the case where I had thermal warm dark matter, okay? In the sense that I have assumed this velocity dependency, okay, where I've used Fermi-Dirac distribution, okay, and I have also assumed this dependency for the temperature evolution since a certain decoupling time. Yes? Mm-hmm. No, we have structure, so we do not want to have a free streaming scale of this size, because essentially it would mean that we would have been able to erase or at least suppress the structure formation at this level, okay? Here, I mean, I would erase them at the level of linear perturbation theory, but at the level of nonlinear perturbation, you can have some of them, but I mean, they will be suppressed. Okay. So the only thing I want you to remember today is that this is only valid for thermal warm dark matter, and as soon as I have another way of producing dark matter, remember in the first lectures, I mentioned freeze-in dark matter or super-WIM dark matter production. If, for example, I have a large mass difference between these two beasts, okay, I can produce my dark matter in the early universe with a non-negligible momentum. That can give rise to dark matter that is non-relativistic at the time of structure formation, okay? And nothing tells me, in that case, for example, as an example, that it's KeV dark matter that is going to be excluded, okay? You have to redo the exercise to know what is exactly the mass scale that is excluded. Now, there are actually somehow other definition of the scale from which, let's say, perturbation are suppressed. And these other definitions come from the transfer function. So you can go still in linear evolution theory, okay? You have your scenario say thermal warm dark matter, and you would like to know what is exactly the linear mode power spectrum into this theory, and what does it look like. You can actually do that by implementing your velocity distribution into a Boltzmann code that is going to evolve the perturbations at all momenta, essentially. And people have been doing this, and they end up with a fit, let's say, to this transfer function that looks like transfer function being the ratio of the linear matter power spectrum in your theory of dark matter, non-cold dark matter, preferably because cold is going to be just one, okay, divided by the power spectrum of cold dark matter at any scale k. This quantity has been fitted for thermal warm dark matter to something that looks like that, which essentially, this is T square K as a function of the scale, and you have a cut into this transfer function, an exponential, no, a cut, around the scale alpha x, okay? Sometimes referred to as breaking scale. Yeah. Yeah. The square root of the scale factor in the wavelength. It's lambda is 2 pi over k. This is a, no, sorry, I don't see. Where? Yeah. K goes as square root of. A over k, 2 pi, square root of 2, 3, v over h. Ah, thank you, sorry. I didn't understand the bracket. You're right. Thank you. Okay. Okay, thank you, sorry. Good, so, notice also that here I have, this is k, so this is 1 over lambda. So lambda free streaming, essentially the scale of free streaming is inversely, scale as the inverse of the mass of dark matter. In the case of this definition of the breaking scale, the scale at which you break essentially the linear mode power spectrum, people have been looking at thermal warm dark matter. How does it look like? And what you end up with is 0.045 kV divided by the mass of the warm dark matter, okay, to the power 1.1 megaparsec over h. Sometimes this is also referred to essentially as a free streaming scale, but it's slightly different definition in the sense that it just comes from a fit of the linear matter power spectrum with respect to of your non-cold dark matter compared to your cold dark matter scenario. So in order to have this fit work, I really have assumed that I have plugged into my Boltzmann code, looking at the evolution of perturbation equation, a distribution function, or more better said, fq times q square fq, okay, you integrate it out, you get number density as a function of q, which will be the momentum, the co-moving momentum, or maybe not the co-moving momentum if this is a temperature of the photon, but okay, time-independent momentum, at least for what we are concerned here. It looks like this for Fermi-Dirac, so you have just one peak, okay, and this is around 3.15. Good. Now you have this linear perturbation theory, you have the linear matter power spectrum, you want to go nonlinear to compare to observation. Observations in particular, the ones that I will refer to here as a reference, are Lyman alpha forest observations. So remember, I mentioned that yesterday. We expect the flux power spectrum of Lyman alpha forest to be suppressed, among other things, at small scales, okay? By comparing the results of hydrodynamical simulation, where you have plugged this information, okay? Either the full linear power spectrum or the transfer function. Once you evolve that along time, together with baryons, in order to account for everything you see, you can essentially constrain the mass of your warm dark matter, okay? Most recent analysis is actually from 2309, 045, 33. So it's Isrik et al. Collaborator. They have been considering a specific bunch of quasar spectra that would arise from quasar between redshift 4 and 5, 4.2 and 5. And with these quasar spectra, they can essentially probe scales, moving distances between 8 megaparsec and 0.23 megaparsecs over h, okay? Just to give you an order of magnitude scale. Thanks to this, they put a constraint MVDM from Lyman alpha observation should be smaller or equal to 5.7 kV at 95% confidence level. Okay? So yeah, we get back to few kV is excluded, okay? But this, not just like from estimating the free streaming length, but really like plugging the linear matter power spectrum into a nonlinear evolution setup and compare really to real observation that you have in order to put a constraint. I repeat, this is only valid in the case of thermal warm dark matter because we have assumed this and we have plugged this in, okay? Good. Now, you can ask me, what do we expect with future probes? There are further possibilities, I mean, more data for Lyman alpha forest. Another potential thing that I've mentioned yesterday is the 21 centimeter cosmology, okay? In case we get to be able to probe the power spectrum of perturbation into the 21 centimeter signal, we get this 3 bump for some scales into the power spectrum, this 3 bump power spectrum, okay? I will put it up there. Maybe this looks too much like CMB, okay, as a function of the scale, as a function of the redshift, remember, for a given scale, say 0.1 megaparsec over h, okay? And the different bumps were related to different period of the history of the universe, the period where stars begin to produce enough Lyman alpha forest, Lyman alpha photon in order to couple the spin temperature to the gas temperature and begin to change the average signal. I didn't mention it yesterday, sorry for that. The global, I mean the sky average signal is actually buried below very large foregrounds, okay? Which means that it's difficult to extract directly this information. You might have heard of the EDGE experiment that I think I mentioned also yesterday, where they had a claim where this signal was extremely suppressed. This claim has not yet been fully confirmed or fully excluded by other experiments, okay? But there are big doubts on the true signal in the sense that, I mean, again, you have to be able to modelize extremely well your foreground in order to be able to extract the cosmological signal. In the case of fluctuations on this signal, the point is that you can expect that the cosmological signal and the foregrounds are going to behave can behave differently for certain scales, okay? At certain scale, you expect the foregrounds to be relatively smooth, while you expect to see some, for example, bumps in the power spectrum due to the cosmological signal. And by looking at these scales, you expect to have a much better handle on really the cosmological signal. This is why I'm mentioning the power spectrum of perturbation. Now, you have those different bumps. This is due to Lyman alpha coupling. This is the period of heating where the temperature was going up above the CMB temperature. And this is the last bump that is related to the time where reionization begins to happen, okay? What would happen if I have non-cold dark matter? That would give rise to a suppression of small-scale structure, okay? These small-scale structure are expected to host stars, okay? And actually, they are numerous. So they provide Lyman alpha flux, X-ray heating, and ionization photon. If you suppress the amount of sources of this type, what is going to happen is that you are going to delay the moment where Lyman alpha coupling happen, where X-ray heating happen, or where reionization is going to happen. So at the level of the power spectrum of fluctuation, what you expect is to have essentially a shift. Okay, now let's try to do that. A shift in the power spectrum, okay? To later time at fixed scale, okay? Again, I show you one snapshot, okay? You have, again, a survey volume, possibly, of a large volume of redshift and scale where you can probe the dependency of your power spectrum in the 21 centimeter perturbation into this, say, non-cold dark matter effect, okay? Obviously, as usual, if it was only cosmology that would give rise to this, it would be fantastic, but we have a lot of astrophysics that can give rise to the same kind of thing, so you have to be, first be very careful into what is exactly the information you plug in. Huh? Do you really plug in the power spectrum? Do you plug a cut in the linear matter power spectrum? Then how do you go from linear to nonlinear? Obviously, you can run expensive simulation, but this has not been done for many cases. Or you use like some approaches like pressure shelter formalism, okay, to count the number of halo per unit mass that has been fitted to some simulations again, which is mostly what people have been using in order to compare what to expect from the data and given a certain effect of non-cold dark matter, okay? What I can tell you is that everything can happen. It might be that essentially you have not much better constraint from 21 centimeter cosmology than Lyman alpha forest observations, or you can improve, okay? The point is that this will depend a lot on the type of stars that you have in the early universe, okay? If you have early stars or you only have stars that, let's say, appear, that we already know of and that we have well studied thanks to UV luminosity data, but at relatively late times, okay? It depends a bit on what is the astrophysics history of our universe. So the only thing I would like to tell you, at the end of the day, about 21 centimeter cosmology constraint on non-cold dark matter, whatever it would be, like axions or a thermal warm dark matter or anything else, there are a lot of assumptions behind it. And when the claim is very strong, I would be suspicious, okay? But this is my bias. Okay, so this is why in the rest, I will essentially refer to Lyman alpha forest constraint as my benchmark for what is the constraint today that I consider like relevant. Good. So this was thermal warm dark matter, and maybe some of you, oh no, yes, yeah. What did I? Yes. Yeah, my capacity. Thank you. K is an inverse of scale. Okay. So now the question I want to ask is, okay, this is all good, fantastic. This is thermal warm dark matter. We come back to the problem of this fantastic thermal warm dark matter that we need 1000 degrees of freedom at the time of decoupling in order to account for all the dark matter, okay? So maybe you don't like it and you want to consider another candidate for, say, another benchmark for warm dark matter. But then, haha, how do you translate all these expensive simulations that have been done for thermal warm dark matter into a new scenario, okay? Or just simply you have a scenario where you have dark matter that is non-cold, but maybe don't look exactly the same. How do I know how to translate, again, these constraints into my new scenario? I will tell you what happened when it works very well, and I will tell you when you cannot trust it, okay? It works very well, actually, when you look at freezing or super WIMP, pure freezing production or pure super WIMP production. So let me just go through what we can guess here. So in this approach, to estimate the free streaming length, I essentially want to know what is the typical velocity of dark matter around structure formation, let's say, roughly around today, okay? So this is what I would like to estimate. And I would like to compare the case of, say, my thermal warm dark matter to any other kind of scenario where dark matter is expected to be produced with some large velocities, okay? And the example we have here is the case of freezing and super WIMP. So first of all, we had this dark matter velocity. Today. And I have the momentum of my dark matter that is expected to scale as 1 over A. And I'm going to introduce the temperature of the photon into the game, because P over T is what I can usually evaluate from my distribution function, from my velocity distribution function. And what I want to do is essentially evaluate this momentum at the time of production of dark matter, okay? At the time of decoupling of warm dark matter, for example, or at the time of freezing for freezing dark matter or whatever, okay? So this I can compute at the time of production, but then I need to scale it to today, okay? The momentum goes as 1 over A, but the temperature of the photon, remember, these scale with 1 over A up to the number of relativistic degrees of freedom contributing to the entropy, okay? So this is not just T naught over M, I forgot the M factor here, but there is actually a ratio of the relativistic number of degrees of freedom between today and the time of production of dark matter to the power 1/3, okay? So this is the quantity that I want to evaluate for different scenarios as a first estimate of how my constraints are going to scale. For warm dark matter, okay, remember the number of okay, I'm also going to work in the situation where I'm going to assume that all the dark matter is made out of non-cold dark matter, okay? If, even in the case of warm dark matter, if let's say I have 20% warm dark matter and all the rest cold dark matter, my cut in the power spectrum is not going to look like that. What I'm going to have is, for example, a cut plus a plateau. The plateau, the position of the plateau depends on the fraction of warm dark matter that you have. Obviously, for these kind of things, you are not going to get the same constraint from Lyman alpha 4S observation, okay? So there have been, again, analysis together with simulation to put constraint on this. they fit sometimes the constraint. I prefer not. I prefer just to send you. I think I have the reference here in the note to papers where you can really see that warm dark matter, even warm dark matter, thermal warm dark matter is not especially excluded at 5.7 keV, right? It depends on the fraction of warm dark matter you have in your bath. Okay. Good. So now let me assume for this that omega dark matter H square and CDM equals 0.12. Okay, so all my dark matter is made of non-cold dark matter. Okay, if it's thermal warm dark matter, this I knew the value, but I mean, let's forget about numerical factor. I just want to, I have 1 over m here, the same 1 over m I had before, but I have taken into account the fact, I mean, I just want to take into account that in the decoupling temperature, I have the number of relativistic degrees of freedom. And if I want to account for all the dark matter, remember, I needed 1,000 degrees of freedom, okay? The exact expression is actually, this is valid for KV dark matter, but it has a scaling with the dark matter mass. The number of relativistic degrees of freedom, actually at the time of production, in order to account for 0.12, if I don't know if I wrote it explicitly, I think, yeah. MKI divided by KV. I mean, this just comes from your thermal warm hot relic abundance that we saw in the first, second lecture. I don't remember, okay? You plug this in here, and you see that you have an extra scaling into the mass, okay? At the end of the day, you see that where your warm dark matter, your velocity of warm dark matter effectively behaves as mass of warm dark matter to the power minus 4/3, okay? So this is essentially the full dependence of my velocity of warm dark matter today as a function of the mass of warm dark matter if I assume that all my dark matter is made out of warm dark matter. Okay, good. So that was for warm dark matter. Now, let's assume that my warm dark matter is produced through the decay of a thermal bath particle B, as we did in the first lecture, that can decay to the dark matter and some, say, standard model particle. And let's assume that they are quite both light compared to the mass of this beast, okay? To first approximation, I expect that the momentum of my particle at the time of production is essentially given by the mass of the bath particle, okay, up to a factor of 2. Okay? Now, the time of production of my dark matter, the time of production, the temperature of production, remember, it was essentially when I had the bath particle that became non-relativistic, okay? So I had production through freezing that essentially freezes around the time where my bath particle become non-relativistic, okay? So temperature of production is just or the order of the mass of my bath particle, okay? And the number of relativistic degrees of freedom here at the time of production are just going to depend on the interaction of my bath, the gauge interaction of my bath particle. So they are essentially independent of the mass of my dark matter. So at the end of the day, here I expect, in terms of mass of dark matter, I just expect the mass of the bath particle just disappear from the equation, okay? It's mb divided by mb. I have m dark matter minus 1 from here, in this case, for freezing. You agree? Yes? And now, in the case of super WIMP, I have the same production. I expect same type of momenta in the same situation, but it's just the time of production that is not the same. Remember, the time of production is when the Hubble rate is of the order of the decay rate of this bath particle, okay? So the temperature of production was actually the square root of m Planck times the decay rate. You remember the geometric mean? It was one of the questions of the test, just for you to put it into your head so that I can repeat it now. Okay, so in the case of superWIM, I have, again, the momentum of my dark matter is supposed to be mb/2, but the temperature of production is just going to scale as the square root of m Planck times the decay rate of the bath particle, okay? So when you plug it in here, again, so this time you don't have the mass of the bath particle that disappear, and what actually pops up is this this ratio that I mentioned earlier, the ratio of essentially, so I'm here, momentum, mb, divided by square root of m Planck, gamma b. This is essentially h at the time. It's essentially this ratio of rate that I mentioned earlier in the lecture. So this is this R gamma, but to the power -1 that I mentioned before. Okay, so essentially the rate of dark matter divided by the Hubble rate at the time where the bath particle becomes non-relativistic, square root. Okay. Okay, times 1 over m chi. And the other depend on gauge couplings of, again, my bath particle somehow, sorry, no. This time, the time of production is, related to this. Okay, so I didn't put any prefactors here. But not just by this, just in this way, what you see is that, first of all, if I have a certain velocity of warm dark matter that is excluded, okay, if I have freezing production, I'm not going to exclude the same masses because the scaling in mass is not the same, okay? So I expect that my dark matter candidate should be smaller in mass, actually, than the mass of warm dark matter to the power 4/3. Whatever the limit I'm interested in, a priori, but I mean, for example, in the case of Lyman alpha forest, time some number, in the case of freezing, okay? In the case of superWIM, same dependency in the mass, okay? It's still m1 over m, but I have another thing that comes into the game here, the relative rate of production. And this is mine, wasn't. Point is, so this is a order of magnitude estimate. What you can do now is you do exactly the same as warm dark matter. You go back to your Boltzmann evolution equation. You extract your momentum distribution at the time of production of your dark matter. You plug it into a Boltzmann code, and you check what is happening and what you are going to exclude, okay? In order to be exactly sure of what are going to be these prefactor, okay? So we'll go here. In the previous lecture, I gave you the Boltzmann evolution equation for the number density of dark matter. At the end of the day, we want to know what is the momentum distribution at the time of production. It's exactly the same, but without integrating over the momenta, the D3P, okay, where we have had the number density. So this you can easily compute by hand. And what you will get, so if you look at your evolution equation of the distribution function, the Liouville operator reduces to this, actually, when I define x as m over t. Remember that the number density I had the n divided by dt, and I had also the derivative through the momentum, okay? I'm going to use a momentum that should be co-moving, okay, with time. So this is the temperature of photon. It's not a good definition because this can depend on time still. Sorry, momentum divided by time. Momentum goes as 1 over a. Temperature doesn't go as 1 over a exactly. There is this, the dependency in the number of degrees of freedom should be p over divided by s to the power 1/3, which should be the best definition, okay? When you do that, essentially, all the time dependency is into the x. And this should be equal to the collision term. The collision terms that depend on the transition amplitude for these processes, for example, okay? The very, very nice thing is that in the case of freezing, you can just have an analytical expression very easily just by integrating out, assuming that the mass of the particle is much larger than the mass of the dark matter and the other potential final state. Also assuming that the bath particle was in equilibrium, is non-relativistic at the time of production, meaning that it follows the Maxwell-Boltzmann statistics. In that setup, it's super easy to extract, actually, a form for this distribution of momentum at the time of production. In the case of freezing, the momentum distribution is definitely not a Fermi-Dirac distribution, okay? You can expect, I will not write all the prefactor. If you want all the prefactor, you can go to the notes. You can expect that the distribution function is just going to be proportional to the rate of production. This doesn't change, this has the number density. I have this R gamma freezing that entered, the com ratio of the decay rate with respect to the Hubble rate at the time where the bath particle becomes non-relativistic. And the dependency in momenta goes actually as q to the power minus 1/2 e to the minus q. So different from a Fermi-Dirac distribution. I have hidden a bunch of stuff under the carpet because I can integrate out this equation, but this q here is actually yet a rescaling of this momentum. I call it q star, and I define it as the momentum divided by some temperature that is related to the temperature of the photon at the time of production, but that I just scale with the scale factor. So this T star is really a 1 over A temperature dependency, okay? And I have a prefactor here that will depend on the typical energy density of dark matter today, on the production mechanism. So this prefactor is actually related to, is one if you have a very large mass splitting between the dark matter and the bath particle and the extra particle in the final state here, A. In the case where there is a non-negligible mass difference, an important potentially MA is near to MB, okay? Then you could have this factor that is slightly different from 1. But at the end of the day, this is the form of your distribution function in case of freezing. If you plot it, overplot it over the Fermi-Dirac distribution, it's gonna look a little bit like that. So point is that at the end of the day, when I have my freezing distribution, I have not a Fermi-Dirac distribution, but I have something that at the end of the day has same kind of behavior. It has one single peak in the Q squared times F distribution. If you plug this quantity into your favorite Boltzmann code and you go through it, you will discover, without much surprises, that it gives rise to exactly same form of transfer functions. What does this tells you is that essentially, given that this was the input of all the nonlinear evolution of my perturbation, I can just translate them, right? Translate them, but with the right dependency of the evolution of these perturbations from the moment of production up until today. The place where this cut happened will just simply reproduce the dependency that we have extracted from looking at this. Except that now I can put a real number here, okay? This happened actually to be 15 keV. Sorry, I should not, let me put it, okay, so this was the, assuming that my warm dark matter mass is 5.3 keV, which was the previous limit, okay, I have 15 keV here. So because I have a different dependency of the momentum with the mass, okay, at the end of the day, I also have a different distribution function. So essentially this should change something, but it doesn't change much at the level of the transfer function. I can very easily translate my constraint from thermal warm dark matter to freezing, okay, and recover essentially this MVDM to the power 3/3 dependency. And actually, when I'm excluding a warm dark matter mass with 5.3 keV, I'm effectively excluding a 15 keV dark matter produced through freezing, okay? So even when I don't have the same production mechanism, it's not especially keV dark matter that I'm excluding or 5 keV dark matter, but it can be larger, okay? This is not very impressive, right? I mean, order of magnitude is the same, 5 keV, 15 keV, but why do we care, okay? So the answer comes with SuperWIMP, okay? You do the same exercise, you compute the distribution function that you will get. Actually, you will get something that is not exactly the same form as SuperWIMP, but which is actually yet producing one single peak in the distribution function. I am looking for my expression, it's here. What you get for SuperWIMP is that it's going to be proportional to this rescale momentum times e to the minus q square. So it's not exactly the same dependency in momenta, yet it will provide a single peaked distribution function, okay? And it will peak at a different momentum, okay? Because it's at a different rescale momentum, because the temperature here is related to the production temperature, okay? Production temperature of superWIMP through superWIMP mechanism does not happen at the time where the bath particle become non-relativistic, but it can happen at much later time, okay? I do the full analysis and I can check that I recover this dependency, okay? And let me now just plug numbers that could give rise to all the dark matter through a superWIMP mechanism within this setup, okay, for the type of Lagrangian that I showed you last time, okay? Interaction of the dark matter through a three-body interaction with a bath particle and a standard model fermion. In that case, in order to have the right relic abundance through superWIMP, you can typically expect that you will need this kind of ratio to be of the order of 10 to the minus 10. And here, the prefactor that you would need would be actually 1 GeV. So what I just want to say here is that even though, okay, we have, at the end of the day, a production mechanism where the dark matter gives rise to a distribution function that is very similar to the one of Fermi-Dirac distribution function, but the production, the moment of the production, the mechanism of production is very different. It can actually give rise to very different dependency of the momenta in terms of the particle physics model that you have been considering. And actually, the one dark matter limit of few kV can translate is actually GeV dark matter exclusion. Okay? You have questions? Okay, so I went through this, and this is very obscure, right? I mean, how could I guess these numbers? Yeah. It has exactly the same kind of form. So it's again one single peak distribution. Sorry? It changed. It changed essentially because Q over T stars is, I mean, a different value. If you want to plot them on the same plot. Okay, now, could I guess this exact prefactor? And the answer is absolutely yes. And I should have begun with that. With this definition of the rescale momentum, considering actually that my so the equation, okay, the growth equation that I was showing you before, actually the sound speed square is much better related to the mean momentum square root, so the velocity dispersion. By taking velocity of dark matter, typical velocity of dark matter today, that should consider that is actually p square root over t. I use this prescription here, and I introduce a ratio of temperature, which is this T star today divided by the temperature of the photon today. I use this precision, I use T, this is the dimensionless, but this is typically the quantity that you have to provide to Boltzmann codes like class, in case you ever played with it. You can actually show this is related to the temperature of production. So you have temperature of production comes here. You have the number of relativistic degrees of freedom between the temperature of production and today that come into the game. Yes. So this is expected velocity, the velocity relevant to compute the constraint on the warm dark matter. So the velocity that I had in my expression of the growth equation, okay? Remember that according to whatever, sorry, P over M, thank you. So you would have, you would see that, would you typically ask the typical momentum divided by the mass and try to estimate this? Actually, this quantity is related to the variation in pressure divided by variation in energy distribution of your dark matter, okay? This is actually, for a non-relativistic particle, directly related to the velocity, to momentum dispersion of your particle, and not directly its average momentum, okay? At the time T0 or the time of structure formation. I do the same game as before. I rescale by the temperature. Okay, I would have a ratio of temperature of production compared to today. Okay. This is typically the, let me use T star at the time of production. Let me use this temperature into the definition, that one. Okay. This is nothing but the typical Q star from your distribution that you can easily compute from the distribution function that you have computed here. Here enters the ratio of what did I write? Time of production. Yeah. I will have the temperature of the photon that should be rescaled, okay, from the time of production until today, okay, which will give me the number of relativistic degrees of freedom, which are essentially written into this quantity, okay. I get at the end of the day, in order for my velocity of dark matter, production through thermal warm dark matter, compared to the velocity of my dark matter, in whatever mechanism I want, where I can compute the mean momentum at the time of production, okay? And I can estimate what is the relevant temperature here, given my distribution function that I can compute also. I get, in the cases where I have a single peak in my distribution, this dependency. So I relate the one I get for warm dark matter, where I can compute every single entry, okay? The momentum, mean momentum at the time of production, and so on. And I will get to compare it to the velocity of dark matter produced through any other mechanism, for example, freezing or superWIMP, and I will end up with this. This is a number, or the one number. This hides the number of relativistic degrees of freedom that is there, okay? And you have the exact value of the warm dark matter mass limit that you have in your scenario. You will have these numbers that fit exactly the number I have provided you. I don't remember where, but the 15 kV for freezing, and the dependency in the relative decay rate in the case of superWIMP. Another question that you can ask is, what happens if we have multiple mechanisms of production, so superWIMP of freezing, that will happen near in time, okay, will give rise to multiple bump in the momentum distribution function, okay? Could have a peak here, and I could have a second peak here, for example, okay? This would give multiple bumps. Can I use this estimate? I actually cannot use this estimate directly, and because this one would be, you would like to use maybe the mean momentum of the total distribution. This would give you not especially a good way to estimate what is the constraint on your scenario. This has been shown through simulations. I mean, people have really been checking that. So these order of magnitude estimates are only valid when you have a single production mechanism that drives essentially all your relic abundance, okay? And drives the distribution function of your dark matter at the time of production. So I will stop here for this lecture. And yeah, that's all I wanted to say. I guess you have a lot of questions. I'm sorry, I've been clumsy today. I really feel tired and unable to focus and to make a clear discussion today. Sorry for that. Do you have any question, or you want precision or something? No? Yes? Sorry? Okay, so by warm and hot, usually people just make the difference between the typical scales that are erased, okay? So, I mean, so hot dark matter was essentially originally just neutrino, okay? And there was not especially the notion, as far as I understand, of warm or hot, okay? They were just like relativistic at the time of production and potentially relativistic today. Was this in agreement or not with structure formation? People very rapidly realized it was not, okay? And that what you need is that the typical free streaming length should at least be smaller than the typical size of the structure that you see, okay? And so essentially, this is why they went to warm dark matter, which was not completely hot, okay? Which is relativistic at the time of production, like hot relics, I mean, thermal warm dark matter, but today it has become non-relativistic and has a certain free streaming scale that is in agreement with the observations. Other questions? Please go ahead. I know I have not been clear, so you are really free to ask all the questions you want. No? Okay. If not, thank you.